So the story of motion in two dimensions basically has two pieces that you need to know. Once you know how to think about motion in one dimension, and in one dimension, what really meant is that something is moving on a straight line, right? So it moves from, let's say, point one to point two like this. And we said, oh, if I know the initial velocity of this object, um, the final velocity of this object is the segment, the acceleration, and the displacement from here to here, and the time interval. These are the five kinematic variables. And if I know any three of these kinematic variables, I can find the other two. That was the story of motion in one dimension. Now, motion in two dimensions talks about sort of more general situations. So you're thinking about things, maybe you threw a ball like this, so it moves around like that. It makes that parabolic shape. That's called projectile motion. Or maybe there's a car that is moving around. So, it goes a little bit east and then it goes north and then takes some sort of direction like that. So you're thinking about objects that are moving freely in two dimensions. And for that, you need to know a couple of things. First, you need to know about vector analysis in 2D. And then second, you need to think about something called the independence of motion. In orthogonal dimensions. And if you get these two right, then you know exactly how to do kinematics in 2D, knowing how to do kinematics in 1D. So these plus kinematics in 1D makes any kinematics in 2D problem very, very easy. So let's start first with the vector analysis story. So we want to understand what it means to think about vectors in multiple dimensions. So let's say I'm thinking about an X and Y coordinate system like this, and then an object, let's say, starts out at this point and then goes around like that, and then ends up at some other point up here. So I think about the displacement always as pointing from the initial point to the final point. So this would be called the displacement vector. And as you can see now, I'm calling it delta R instead of calling it delta X like I used to, because it's no longer movement along X or Y alone, but it's movement in both directions. Now, what we call the projection of this displacement in the X direction, that we call delta X. So that's the component of the displacement in the direction that is called X. We call that the displacement delta X. The component that is in the direction of the y-axis, we call that the delta y, the displacement in the y direction. So you can see that the displacement in two dimension can be thought of as displacements, two displacements in one dimension. One of them is in X, and one of them is orthogonal to it in Y. And I mean, X and Y could be any axes depending on the problem. Your choice of X and Y could be different. So let's say you have something that is sliding like this down an incline. So maybe you'll choose your X like this and your Y like that, even though this is the direction of gravity, for example, right? So your choice of X and Y coordinate system will depend on the kind of the problem. I'm going to keep drawing them horizontal and vertical like that, but just keep in the back of your mind that X and Y could be in any direction really, as long as they're orthogonal to each other. So the displacement vector can be thought of as two vectors like that. You can also think about a velocity vector. So let's say a car is like here and you're looking at it from the top, and this car is moving something in the east and something in the west. So it has some velocity vector like this, indicating its magnitude and the direction. So it's going 60 miles per hour, let's say, northeast or something like that. Now this would have some component of the velocity that is pointing in the east direction and some component of the velocity that is pointing in the north direction. So you can think about the velocity vector as having two components, X and Y. I keep calling these quantities vectors because that's precisely what they are. A vector is any quantity that has magnitude and direction. Right? So the direction information here is important. A car is moving 60 miles per hour northeast is different than a car moving 60 miles per hour, southwest. These are two different velocities. And the components here are related to the directions of the axes relative to the direction of the vector itself. So the displacement is a vector, the velocity is a vector, it has magnitude and direction, as we've said before, and the acceleration is also a vector. So let's say you have a car like this, and let's say it's moving in some direction, but let's say it's slowing down, so the acceleration is in the opposite direction. So let's say this is the direction of the acceleration, because the car, it's hit the brakes, so it's slowing down. So that means that the acceleration vector would have some component in the x direction and some component in the y direction, because it's a vector quantity that has magnitude and direction. So what we want to learn, first of all, this is sort of the motivation of why we learn vector analysis. And what we want to learn is, for just any vector representing any of these quantities or any physical quantity that is a vector really, how do I go from specifying magnitude and direction to specifying these things that we're calling the components of the vector, delta x and delta y, or in this case, it'd be ax and ay. So let's say this is my coordinate system again, x and y like that. So this would be the x component of the vector a, and this would be the y component of vector a, where a is a vector really that represents any physical quantity. It could be velocity, could be displacement, could be acceleration, could be anything else. We'll see later in the course, it could be momentum and so on. So there are 4 pieces of information about any vector. 2 of them are sufficient to identify that vector. So for example, vector A I can specify by magnitude and direction, or I can specify by the x and the y components. These are called the components of the vector. So these 4 pieces of information, 1, 2, 3, 4, magnitude, direction, x and y components. If I know any 2 of those, I can find the other 2. And typically it looks like this. You either know the magnitude and direction and you're trying to find the components, or you know the components and you're trying to find the magnitude and the direction. So we're going to learn today how to do that, to go back and forth when knowing the magnitude and the direction. But first of all, let's specify in this coordinate system here, here's what I'm calling the magnitude. The magnitude is the length of this vector here. That's the magnitude. And we typically refer to it with just the letter without the arrow on top. That's the magnitude. It's just how big it is without really reference to the direction information. The direction, typically we're going to take it starting from the x-axis and you're going counterclockwise. That's what we call the direction of that vector, theta sub a. That's the direction. So the magnitude is just how long the vector is. The direction is going from the x-axis counterclockwise. This angle is called the direction of that vector. The x and the y components are the projection of the vector on the x and the y axes. Let me show you this simulation that you can play with to understand the relationship of the vector, its direction, and to the components. And then we're also going to use it to verify our calculations in a minute. So let me just start that simulation. So if you just look for Fed vector addition, you'll find it. It's that first answer here, and it's from the University of Colorado website, a simulation about vector addition. So this is the one that we're going to use to play around with vectors and see how to handle them and add them and all that. So suppose I want to think about 2D, vectors in 2D. And maybe I'll just start with putting a vector here, any vector in any direction. Now you see there are 4 pieces of information up here for that vector. As long as I'm selecting a vector, the information is up here. First, it's the size of the vector, or the length of the vector, or the magnitude of the vector. And then there's the angle from the x-axis going like that. So this angle here would be the 53 degrees down here. And then the x component. So you can count 1, 2, 3, 4, 5, 6 units. That's the x component of that vector. And then the y component of the vector, you can count them 1, 2, 3, 4, 5 up to here. And then 1, 2, 3, that's 8. So that's the y component of the vector, right? And you can show these components like that. Or there's another way you can represent them. It's equivalent representation. As you see, I can just represent the y on that side. And the way people sometimes do that is so that the x part is on the x-axis and the y part is on the y-axis. but it's just as equivalent as this one. And if the vector is not at the origin, it could be anywhere. You can also think of these x and y components as being the projection of the vector. So think of some light that is shining from this side, and it shows the shadow on the y-axis. That's called the y component. Think of light shining from above, and it shows the shadow on the x-axis. That's called the x component of that vector. So any of these representations is equivalent to represent the components, because these are not physical things. This is actually just the tool that we use to analyze these problems. So you can understand the components of the vectors. Okay. Now I can bring another vector here, and you can look at its components too. And we can try to think about how can we go from magnitude and direction to x and y components. So let's sort this out, and then we'll come back and we'll play with some of these vectors. We'll make some vectors and see if we can actually figure these out. So the analysis here uses something that you know and love, which is called trigonometry. So here's a refresher of trig, all the things that you need to know about trig in this course. We're not going to use extensive things about trig, so none of like the double angle formulas and all of that stuff, all of that fun stuff. All we need is just the definitions of the sine, the cosine, and the tan functions. That's all we need. So you say, okay, the size of this side here, that's the magnitude of the vector. So I write it without the arrow on top, as you've seen in the simulation and in other places, you'll see it. People write it like that to represent the magnitude of the vector, just how big it is when they put the things on the side. The way I do it is just I drop the arrow on top, and that represents the magnitude for me. And then let's say this is the x component, and this is the y component, and this is the angle. Now, because x and the y axes are perpendicular to each other, so that means this is a right angle. And right angle triangles, we know how to handle from trig. We know that I can write something called the sine function, which relates the ratio of the sides to the angle. So you might know a mnemonic that would help you figure this out, but the sine function is always about the ratio of the side that is opposite to the angle. So when I'm thinking about theta here, the opposite to it would be this one, because these two are next to it. But the one that's opposite to it is AY. And then that's divided by the hypotenuse, and the hypotenuse is the one that's opposite to the 90 degrees always. So that's how we define the sine function. And this function is a function that takes you from the angle to the ratio of the sides. Now, if you have the ratio of the sides and you want to find the angle, then you do something called the inverse of that function. And the inverse of that function, it's called the inverse because it inverts the action. So I can go from theta to the ratio of the sides. That's called the sine function. Or I can go from the ratio of the sides to the angle, and that's called the inverse of that sine function. So the inverse here doesn't necessarily mean the inverse that you're used to, where you say x to the inverse like that is just 1 over x. That's not the case when you're thinking about the trig functions. The inverse in this case just means go back. And sometimes it's represented as a sign like that. Okay, you'll see it in some calculators written like that, to mean arc sine. Okay, and then other functions, other trig functions that relate to other sides. So for example, you can talk about the cosine function, and the cosine function relates the side that's next to it, the adjacent to the hypotenuse. And of course, again, you can do the inverse function that takes you back from the ratio of the sides back to the angle. You could also talk about something called the tangent function, or the tan function, which is just the ratio of the two. It's just sine theta divided by cosine theta. And if you work that out, it's this function divided by this function, so it gives you AY over AX, which is the opposite divided by the adjacent. And again, you can do the inverse tan function, go back from the ratio of the sides back to the angle. And already you can see that it's, you can get the angle if you know the components, because the components are x and y. So if I know the components of any vector, ax and ay, I can always find the direction of that vector by doing the tan inverse like that. So this equation is one of the most important ones in these 6 for us. We use all 6, but this one is sometimes the most important one because if you know the components AY and AX, you can always find theta. And A, like we said, represents anything. So it could be, you know, suppose you want to find the direction of some velocity vector, and all you know is the X and the Y components of that vector. So you say, if I know the X and the Y components of the vector, I can find the direction here by saying that theta is the tan inverse of the Y component of the velocity compared to the X component of the velocity. Okay. So we're going to use all of these trig functions when we're thinking about how to convert from one thing to another. The one last thing that you need to know before we actually do some calculations of vectors, the last thing you need to know, and maybe we'll just add it down here, is you need to know the Pythagorean theorem. So Pythagorean theorem. And the Pythagorean theorem relates to right angle triangles, and it says the following. It says, suppose I have a right angle triangle like this. It's one of the earliest theorems in geometry, and it's a really fantastic one because it says, suppose I have a right angle triangle like this. Then if I build a square on this side, and a square just means take this side here and put the same side on here. So if I call this C, this is also C. And if I also draw a square on this side, so if this side is called A, then this would also be A because it's a square. And if I draw a square on the third side, like this, that's called B, let's say. So what the Pythagorean theorem says is that if you add up this angle and this angle, this area and this area. So if I add up this area, which is, of course, the area of a square is multiplying the two sides by each other. So the area here would be A squared. The area here would be B squared. If I add up these two areas together, I get the area of the big square here on the hypotenuse, which is C squared. So really this says that C squared is equal to B squared plus A squared. That's the Pythagorean, which is the area of the square that is drawn on the hypotenuse is equal to the sum of the areas of the squares drawn on the other two sides. So that's all we need to know trig-wise, Pythagorean theorem-wise, to be able to go from components to magnitude and direction, and from magnitude and direction to components. So let's try that. Suppose I have a vector B, like that. And suppose it's in a coordinate system that I'm going to draw sort of crooked on purpose here so that I don't want you to get used to just X and Y being horizontal and vertical. Just think this is any direction really. So the X component of this vector is going to be parallel to the X axis, and the Y component of this vector is going to be parallel to the Y axis like that. And the direction is always from the X towards the vector like this. What I know is, let's say I know the magnitude of the vector and the direction of the vector, and I want to convert that to the X and the Y components. And then a little bit later, we know the X and the Y components, and we want to figure out the magnitude and the direction. So let's start with the first story here. How do I figure out the components if I know the magnitude and the direction? Well, one way to do it is to recognize that these three things, for example, the X and the theta and the magnitude of the vector are related by the cosine function here. The cosine function says it's the adjacent divided by the hypotenuse. So if I say cosine theta is equal to the adjacent, which is the X component, divided by the hypotenuse, which is the magnitude, then I can multiply both sides by the hypotenuse magnitude, and I get this. So I found the X component by knowing the magnitude and the direction. I could do the same thing with the sine function. You can say that the sine function is equal to the Y component divided by the hypotenuse because the y component is opposite to the angle divided by the hypotenuse, which is the magnitude, and multiply both sides by the magnitude, I can get that the y component is equal to the magnitude times sine the angle. So this is the way to find the x and the y components of a vector if I know its magnitude and its direction. Let's try that with the vectors in the simulation here. Let's see if I can figure out these two components here, let's say for B, if I know the magnitude and the direction here. So let's do an example. So the length of B is 10 and the angle is 37 degrees. So I draw the triangle and I say this length is 10. It's the magnitude of the vector, and this angle is 36.9 degrees, and I'm trying to find these two sides, the x component and the y component of the vector. So I say, well, you know, I can do this thing. I can say cosine the angle is equal to bx divided by 10. Multiply both sides by 10, I get bx to be 10 times cosine 36.9 degrees. And that will give you, if you work it out, it will give you 8. It'll give you 8. Because cosine 36.9 is 0.8. So that'll give you 8. Whatever these units are. Because remember, this could be representing anything. Could be representing a displacement, in which case this might be meters. Could be representing a velocity, in which case this might be meters per second. It could be representing acceleration, which might be then in that case meters per second squared. And then I can also calculate the y component similarly by multiplying the magnitude by sine the angle. And sine 36.9 is 0.6. So this gives me 6. And again, this could be any units depending on whatever physical quantity. It could be displacement, velocity, acceleration, momentum, whatever. So let's check if this is the right answer here. X is 8 and y is 6. X is 8 and y is 6. Very nice. Suppose I want to do the other way around. Suppose I know that the x is 8 and the y is 6, and I'm trying to get back that 10 and that's 37. Or maybe we want to do it for the a this time. So suppose I know that ax is 6 and ay is 8, and I'm trying to find the magnitude and the direction of it. How do I do that? So that's this case here. I know the x and the y components of a vector, and I'm trying to find its magnitude and its direction. So again, we go back to our relationships that we've discovered with trig, and we say, if I know the x and the y and I'm trying to find the magnitude, what can I do? That's like saying, I know the two sides of a right angle triangle and I'm trying to find the hypotenuse. So that's using the Pythagorean theorem, I can do that. I can say that the hypotenuse, which is just the magnitude of the vector, is equal to, so the square of that is equal to one side squared plus the other side squared. So that's the x component squared plus the y component squared, just by the Pythagorean theorem. So if I really want to just find the magnitude, it would be the square root of the x component squared plus the y component squared. On the other hand, if you want to find the angle, then you say, what do I know about this triangle here? I know for this angle, I know the opposite and I know the adjacent. And when I know the opposite and the adjacent, the easiest thing to do to find that angle is to use the tan inverse. So you say, I know the opposite, I know the adjacent, I can find the angle. So tan theta is equal to the opposite divided by the adjacent. So that means the theta itself is the tan inverse of the opposite divided by the adjacent. And that's it. There you have it. If you know the magnitude and the direction of a vector, you can find the x and the y components using the trig functions, cosine and sine. If you know the x and the y components, you can find the magnitude and the direction using the Pythagorean theorem and the arctan function. Let's see if we can do an example and figure this out. So suppose ax is 6 and ay is 8. What is the magnitude and the direction? Say, what are the magnitude and the direction of that vector? Also, let me draw it. The x component is 6. The y component is 8. So then this here is the magnitude, and I want to find this one, and I want to find this one, the angle. So the magnitude, I can use the Pythagorean theorem here, this one. So I can say then the magnitude of the vector A, which you can write like this or you can write like this, is equal to the square root of the squared sum of the components. So in this case, it'd be the square root of ax squared, that's 6 squared, which is 36, plus 8 squared, which is 64. 36 plus 64 is 100. So this is square root of 100, which is 10. What about the angle? I can use the tan inverse angle. Okay, thank you. I can use the tan inverse of the to find the angle. So this is the tan inverse of the opposite divided by the adjacent. So that's 8 divided by 6. Yeah, that's the 53 degrees. You can work it out. Maybe it's useful if you try now and put it in your calculator just to make sure that you get this number. If you don't get this number, maybe change the setting. Just make sure that the mode on the calculator is set to degrees instead of radians to get the answer in degrees. You can get the answer in radians if you want to, and then you can convert from radians to degrees, and we'll learn that conversion later in the term. If you want to learn it now, it's really easy. Just look up conversion from degrees to radians and radians to degrees. But for now, we're just using the angles to be degrees. Okay, so let's check that we got the 10 and the 53. So let's go, yeah, 10 and 53. Very nice. Okay, there are a couple more things to say about vectors, which is that you can have a vector. Let me erase this. Let me just take one of these vectors and then let me make the vector point like this. Now notice one thing here. Notice that the x component of this vector came out negative. What does that mean? When I have a negative x component, it means that that particular component is pointing opposite to the direction of positive x. See, the y component is still pointing in the direction parallel to the positive y, so that's positive. But the x component is pointing in the opposite direction of x, so that's negative x component. I can also make both negative. So here the x is pointing opposite to positive x, so it's negative. And the y is pointing opposite to what I'm calling positive y, so it's also negative. So the direction of the vector will tell you what the components are like. You know, positive and positive, or negative and negative like that, or you can get in between. You can get x is positive, y is negative, and so on. This particular kind of vector, the c vector, is a really interesting one too, because it does not have any extension in x at all. So its x component is 0. You can also make a vector whose y component is 0 by pointing it this way. So pointing parallel to the x direction, that means you have no extension in the y direction. See, if you think about shining light, so for example, if I look at, is there trash somewhere? Yeah, here we go. So if I look at this vector b, and I shine some light from the right here, to look at the projection on y, I see nothing. It's basically a dot. So it has no extension in y. That's why the y component is 0. But it has some x component, because if I shine light from up here, I'll see a shadow down here. So if I look at its components for b, I get some component here, but no component in y. C, on the other hand, has some component in y, but it has no component in x. See, its x component is 0, and its y component is negative because it's pointing opposite to the direction that I'm calling positive y. So components can be positive or negative, but the magnitude can never be negative. Magnitudes are always positive because magnitudes are about the size of something or how big something is. So magnitude is always positive, but components can be positive or negative depending on my choice of the axes and whether the vector has components that are pointing opposite to the direction that I'm calling positive or in the direction that I'm calling positive. So this is the story of vector analysis going from components to magnitude and direction, and from magnitude and direction to components. The very last thing we want to say about vectors is how do we add them? How do I add vectors? Now, why do we need to do that? Because sometimes I need to think about adding vectors. For example, one of the kinematic equations says something like this. So this is a vector that I'm multiplying acceleration by time here. Time is a scalar, so it just scales the vector. And then I'm adding it to another vector to find the third vector. So we need to think about vector addition. You don't have to worry about this for now. I'm just motivating why we need to think about vector addition. So you say something like, suppose I have a vector C that is the sum of the vectors A and B. How do I find that? Let's say vector A looks like this, and vector B looks something like this. How do I find vector C? Well, there are a couple of things that I need to tell you beforehand, before I tell you about the addition. One is that the vector is only defined by its magnitude and direction, so it's not really defined about where it starts. So if this is B, this is also B. This is also B. This is also B. This is also B. See, as long as it has the same size and pointing in the same direction, that's exactly the same vector. It doesn't matter where you place it on the surface here. You can place it anywhere you want. The same is true for any vector. So if this is A, then this is also A. Well, it's supposed to be pointing in the same direction. This is A, this is A, this is A. Oh, it has to be the same size. So as long as I can take that vector and place it anywhere else, that's the same vector. You don't have to start from the same point. Okay, so how do I add A and B? There are two methods. One is called the graphical addition, which you need to understand because conceptually it is how you think about it. But then really how when you're calculating problems and so on, you're going to use the component method. So there are two methods, graphical, also known as tail to head, and a component method. Let's think about the graphical one first. How do I do graphical addition of vectors? How do I find C if I know A and B? Well, here's a simple way of doing it. First of all, you start with the very first vector. You say C is equal to A plus something added to it. So I'm going to start with A. So what I do is I take that A and I draw it somewhere else. So I can just copy it if I want. Put it right here. It's the same exact vector. I didn't do anything. And then I take the vector next in line and I draw it, but I draw it in a special place where its tail is on the head of the first vector, like that. So the vector C, which is the sum of A and B, starts from the beginning, from the very first vector, and ends at the end of the last vector. So that's C. And the direction here is important. Notice that it's not like this. It doesn't close the thing. It's actually starts from the very beginning and ends at the very end. And what this is really saying, this equal sign is saying that suppose this is a displacement story. So suppose A and B and C represented displacement. What the equal sign is saying that the displacement by doing this trip is the same as the displacement by doing this trip. If you remember the Valencia east and west trip, you could take any route, but the displacement was the same. So what this equal sign is saying is that you could take the trip A and then B, or you can just take the trip C. It starts at the same point and ends at the same point. That's what it's saying. What if I want to think about three vectors? So A, B, and let's pick another vector like this. Let's call it D. And I want to ask, find some vector R that is, let's say, A plus B plus D. How do I find that? Well, the same method. First of all, R starts with A, so I'm going to take that. That's going to be my first one. And I can draw it anywhere else. I can redraw it, but it's simple for me to just copy and paste because it's already on my page. But you can just redraw it if you're drawing it with pencil and so on. And then I'm going to take the second vector in line here. So that's A and then B. So I'm going to take B. I'm going to put its tail right on the head of A. And then after that, I have D. So I'm going to do the same thing. Oops, I didn't copy it. Should have just copied it and left the other one. I'll just leave B here because we're using. And then I'm going to take D as well because that's the next in line. And I'm going to paste this such that its tail is right on. So where is R? R is the vector that starts at the beginning of the first one and ends at the end of the last one. So it starts from here. Let's find another color. So it starts from here and ends here. That's the vector R. And so on. If I wanted to add another vector, E, then I would add E here, and then this would be the sum A plus B plus D plus E. Want to add another vector, you add another vector, and so on. So you add vectors by putting the tail of the second vector to the head of the first one, and then the tail of the third one on the head of the second one, and the tail of the fourth one and the head of the third one, and so on. You just keep putting tail to head. And notice that it doesn't really matter which direction they're pointing, left, right, up, down, you know, you just keep adding them like that. And then the sum in the very end is always from the very beginning to the very end like this. Notice that it doesn't close it. It starts where the start is of the whole story and it ends where the end is. That's the sum. So you can say take the purple route or just take the blue route. These two are equivalent. So that's how you do graphical addition. What if I want to say something like, suppose I take these three vectors again, and I want to say something like, find the vector P, which is A plus B minus D. What's that minus sign? What does that mean? What is the minus of a vector? The minus of a vector is the same magnitude as the vector. So the magnitude of minus D is the same magnitude as D itself. So they have the same size, but they're in the opposite direction. So the theta of that vector is the theta of the vector itself plus 180. What does that mean? It means just flip the direction. So if this is the vector D, if this is D, minus D would be the same size, but in the opposite direction. So the arrow is not pointing this way, it's pointing the other way. That's negative D. That's all it is. Just flip the direction to the other side. So the same size, but the arrow is pointing the opposite way, right? If this is the vector A, then this would be the vector negative A. Just same magnitude, but pointing in the opposite direction, okay? So how do I add these? Well, you can think of this as A plus B plus some vector called minus D. And just apply the rule as before. So what do? You carry A and B. So suppose I take everything, put them here. So first of all, I'm going to just take D out of the way here. And I say first A plus B. So I take B and I put its tail right on the head of A. And then I want to add to that negative d. So I don't need the arrow on this side, I need the arrow on the other side. And then I can take the tail and put that here. That's negative d. So this is the start of A, and the end of negative d is here. So this here is the vector P. See, the arrows are really important. Which direction the arrowhead is really critical. So that's how you do vector addition with figures. The graphical method is you just keep putting tail to head, tail to head, tail to head, and then at the very end, the sum of all of the vectors would be starting from the very beginning of the first one to the very end of the last one. That's how you do the graphical addition. So for example, if we're looking at the story here and we say, how do I add, let's say I have vector A and vector B and vector C. Let me just take out the components for now so that it's clear. And let's just make it be like that and C like this. And I say, how do I add A to B to C? Well, first I bring A. I can put it wherever I want. I don't need to start any specific place. But maybe for simplicity, maybe I'll just start here. Right. And then I'll take B and I'll put its tail right on the head of A because I'm adding A to B to C. And then I'm going to add C to them like that. And then I'm going to look at the sum, and the sum is going to be the vector that really goes around like that, starts from the very beginning, ends at the very end. And you can see that if I change the direction of C or the angle of C, the sum is always pointing to that. Change any of these vectors like this, you'll find that the sum is always the one that starts at the very beginning and ends at the very end. Now, from this, you can actually notice how to do it with the component method. Let's just take one of the vectors out so that it's easier to see. Let me take C out of the picture, and I'm just adding A and B. We'll see how you can do it with 3 vectors. It's the same kind of story, but it might be easier to just see with 2 vectors. So suppose this is A and this is B. So the sum of the two would be this vector S here. And you want to ask, what are the components of these vectors? And how do I think about adding the components? So here's one way to see it. You see the components of the vector A are right here. Let me just take the sum out for a second. Here are the components of the vector A. The X component is a projection. The B component is the projection on X and the projection on Y. So these are the Y components of A and B, the X components of A and B. And then you ask, what are the X and the Y components of the sum? Maybe this is an easier way to see it. Okay, so these two here, this one is the X component of A, and this one is the X component of B. And then this darker blue one is the X component of the sum of A and B. And you can see that the X component of the sum is equal to the sum of the X components. And the Y component of the sum is equal to the sum of the Y component. And that's exactly what we say. So for the component method, we say that if R is equal to A plus B, then that implies that the X component of R is equal to the sum of the X components of A and B, and the Y component of R is equal to the sum of the Y components of A and B. That's all it is. So we can practice that, can figure it out. So let's start with vector A. Vector A has 6 and 8. So vector A can be described by the x component is 6 and the y component of A is 8. What about vector B? Well, vector B can be described by x is 10 and y is 3. So we say here the vector S is the sum of A and B. So that implies that the x component of S is the sum of the x components of A and B. So 6 and 10, so that's 16. And the y component of S is the sum of the y components of A and B. So that's 8 plus 3, so that's 11. So I'm expecting S to be 16 and 11. Let's check that. 16 and 11. Very nice. Now, here's another complication that might happen sometimes, is that the vector B could be a vector that has some component that is negative. Let's say its y component is negative. So see that the y component is negative 6 like that. How do I handle that case? Well, in that case, I take the y component of A, which is 8, and I add it to the y component of B, which is negative 6. So that's 8 plus negative 6, that's 2. 8 plus negative 6 is 2. So I expect that the y component of S would be 2. The y component of S would be 2. So if one of these is negative, then it doesn't matter. You just keep adding things with their signs. So if by was negative 3, for example, then this would be 8 plus negative 3, so it would be 5, and so on. So that's how you add the vectors with the component method. So we've learned about vectors. They have some magnitude, direction, and components. We learned how to convert from x and y components to magnitude and direction. We learned how to convert from magnitude and direction to x and y components. Sometimes they call it decomposition of the vector. You take magnitude and direction, you decompose it into components. We also learned about how to add vectors or subtract vectors using two methods, the graphical method and the component method.